event is about. As you know, the Simons Institute hosts thematic programs every semester on a wide range of topics. And associated with each program, there are many research fellows. We can be postdocs, junior faculty elsewhere, sometimes senior students. And in addition to that, we also have running pods in quantum computing and machine learning, which has their own postdoctoral fellows as well. So put all this together, the Simons Institute is lucky to have probably the largest concentration of postdocs in theoretical computer science, broadly construed, all converging at one place at any given time. So, and in fact, the research fellows are in some sense one of the shining jewels of these programs, because they really have a lot of energy. They're brimming with ideas, push the frontiers, as you can imagine. And we one of the things we do at the beginning of each semester is to have this event where we invite the fellows in the program and any other fellows who are here longer term to give talks on their research. And the idea is, the talks are brief, so the idea is it's more like an icebreaker. So you learn a little bit about what they are interested in. They can, and some of the talks could even be invitations to collaborate, or, open problems. The format is up to them. And we have an exciting schedule of talks today. So the program is a little bit shorter this semester because we have only one program running currently in meta complexity. So we will wrap this up in the morning session. Normally it's an all day or even a longer than a day event. So we have two sessions today, the first session with 5 talks and the second session with 4 talks. And so let's get started with the first talk by Yuval Dagan on adversarial laws of large numbers and connections to online classification.
Hey. Yeah. Okay, yeah. So yeah, this is more like statistics or like a learning theory topic. So I'll talk about, and it's connected to also streaming algorithms. So I'll talk about a specific work. It's called the Adversarial Laws of Large Numbers, a collaboration with Noga Alon, Omri Ben Eliezer, Shai Moran, Moni Naor, and Elon Yogev. So I will talk about 3 things. So first of all, I will talk about an online sampling setting where there is some sampler that is competing against an adversary. Then I will talk about online learning, and I will talk about the connection between these 2 settings. So the motivation here is that we have a very large amount of data and like a stream of data. And there is an algorithm that doesn't have resources to see all the data. So they can just see a small fraction of the data, and they want to analyze the whole stream using only their subset. For example, maybe you have an internet adapter that gets a lot of traffic data, and they want to analyze what's happening in the network, but they can only sample a small fraction of it and analyze it. So here is like the algorithm that we're going to analyze. So we have a stream of data points, and there is an algorithm that decides for each data point if they want to store or discard the point. So they're going to store every point independently with some small probability p, and then otherwise discard it. And the algorithm only has access to the points that they sampled. And now, before describing the adversarial setting that I'm going to discuss, let me first compare it to the classical assumption. This assumption was used to analyze classical streaming algorithms. And this assumption assumes that the stream of examples is fixed ahead of time. So there is maybe the stream, the order of the elements in the stream can be adversarial, but the classical assumption was that the algorithm cannot interact with the stream. So the elements were fixed, but this assumption is not realistic because the algorithm can interact with the stream. For example, you have an online store and you want to analyze it. So you analyze the stream by collecting statistics, but then after analyzing the stream, maybe you change your inventory, change your prices, and thereby you interact with the stream. And there are many other examples. So we want to have a different notion of stream that is adversarial. And this was suggested by Ben Eliezer and Yogev. So here there is an adversary that generates a stream. And in this setting, we assume that the adversary knows everything about the algorithm. So the adversary knows the internal state of the algorithm. And in this talk, this will correspond to the adversary knowing exactly what points were sampled. So the adversary will start by generating the first point, and then they see if this point was sampled. And based on that, they they decide what is the second element in the stream, et cetera, et cetera. So the adversary knows exactly what was sampled, and they adapt the stream based on whatever was sampled. And here is the, so now we have, we defined the adversarial stream. And now I'll explain to you what is the goal, what is the algorithmic task that we want to solve in this work. So here we have multiple statistics of the stream. So each statistic is just like a statistic function. And we want to know the average of each of these functions on the stream. But we only have access to a sample. So we will just analyze an algorithm that is computing the average of each function on the sample, and we'll use it to approximate the average on the whole stream. And our goal is to get all these functions correctly. So we have like a class of functions, and our error will be the maximum over all the functions of the difference between the average on the stream and the average on the sample. And why is this maximum an important notion? For example, maybe you want to run some algorithm that uses all these statistics. And even if you get one statistic wrong, you can fail the algorithm. For example, like you want to route cars over some network, like you have, you're a GPS system, you want to route cars. And if there is one congested network that you make a mistake there, then maybe you're going to send all the cars over there and you are screwed. So like in many cases, you really want to get all the statistics correctly. So this is the task, and our goal would be, so we want a sample such that for all the statistics, the error is going to be bounded by epsilon, and this is with probability 1 minus delta, and the probability is taken over the randomness of the algorithm. So first, let me describe some prior works. So first of all, in the classical assumption that the stream is fixed, the answer is very easy. So we want to know like how big should the sample be, and in the classical assumption, the length of the sample corresponds to the VC dimension of the class of functions, and the VC dimension is a combinatorial property of the class of functions that is used for learning theory, and this follows directly from the fundamental theorem of pack learning. And now for adversarial stream, Ben Eliezer and Yogev showed that the VC dimension might not suffice, and they also showed an upper bound that depends on the log cardinality of the class of functions. But now the question is, what happens if the class of functions is very large or infinite? Maybe we can get better dependency. So we want a smaller sample in general. And in this work, we show that the sample size that you need is up to constant factors, the Littlestone dimension of the class of function that we want to approximate. And here, Littlestone's dimension is essentially another combinatorial property of the class of functions. And this captures the error in online learning. essentially. So we connect the sample complexity to a different quantity that is called Littlestone's dimension of the class of function. And as an application of the proof, we also show an optimal bound for online learning. And here we improve a logarithmic factor for learning with 0-1 losses. So how many minutes do I have left?
Maybe 3-4 minutes.
Okay. So let me explain briefly about the proof. So and I want to explain how the adversarial sampling connects to online learning. So there is this notion of sequential Rademacher complexity that it was defined by Rachlin et al. And this notion, they showed that it bounds the regret in online learning, like the error in online learning. And they got a bound on this notion, the sequential Rademacher complexity. If you're familiar, it's an analog of the Rademacher complexity that is used in classical learning to the online learning setting. And in this work, we bound the error in sampling by the sequential Rademacher complexity, and we get a tighter bound on the sequential Rademacher complexity, and thereby we also improve the bound for online learning. And now let me explain to you like what are the main like proof ideas. So first of all, I want to explain how the sample complexity is bounded by the sequential Rademacher complexity. So let me tell you what is the sequential Rademacher complexity. So essentially, the sequential Rademacher complexity is equivalent to the error in adversarial sampling, where you sample each element with probability 1/2. So in the original problem, we sampled each element with a very small probability because we have a really small sample compared to the large stream. But here we want to reduce from a very tiny sampling probability to a sampling probability of 1/2. And the way you do it is you look at another, what is called like a ghost sample. So, and this another sample, you draw it for the analysis, and then you compare the true sample to the ghost sample. And by some simple reductions, we can show that it's sufficient to bound the true sample to the ghost sample, and then we can ignore the rest of the stream, and we have a much smaller stream where the sample is just a half of the smaller stream. And now we reduce the sampling problem to the problem where you sample everything with probability 1/2, which is also corresponding to the sequential Rademacher complexity. And now, in order to bound the sequential Rademacher complexity, so what people usually do, they use the notion of what is called covering numbers. So covering number is the smallest size of an epsilon net on the class of functions. And in the online setting, it was very, in the adversarial setting, it's hard to get good bounds on the covering numbers. So here we show relaxation of the covering numbers, which is like fractional cover. So we have a distribution over cover elements. And with this relaxation, we can get better bounds. So these are the main proof ideas. So now let me summarize. So I explained the adversarial streaming model, where you compete with an adversary rather than a stream that is fixed ahead of time. And the goal is to approximate multiple statistic functions. And here we showed what is the optimal sample size. And we also got tight bounds for online learning. And for the proof, so we show how to reduce to the notion of sequential Rademacher complexity. And we use a notion of fractional covering numbers rather than the classical covering numbers. And also there are some open problems. For example, we can look at weaker adversarial models, maybe models where the adversary doesn't know everything about you. Maybe the adversary will know less and you want to compete with them. And we can think of other sampling tasks. Maybe you want to compute some more complicated functions of the stream. And maybe and there are other problems one can think.
Time for maybe a quick question.
Yeah. Find the class of statistical tasks that your result applies to.
Can you repeat the question?
Yeah, it's a class with 0, 1 function, like the value is 0 and 1. It can be any class. And
function of the sample.
Yeah, class of 0, 1 function. And because you're competing against an adversary, so the notion of a little stone dimension characterizes exactly what is the sample that you need against an optimal, against the best adversary, essentially, against the worst adversary.
Thank you very much.
Thanks again, Yuval. And next talk. Next talk is Quantum for Science by Jinpeng Liu.